All right, hi y'all. I guess today, or the second video today here, we're going to be going over bounce diagrams and EM waves. So this is a problem from a past exam, problem 3, and this is typical of what you would see in problem 3 for, I guess, this EM for exam 1. Now, let's get an idea about what this problem's asking us. So it says a voltage source is applied at the left end of a transmission line as shown below. A plot of the generator voltage is shown below. The pulse width is W is equal to 2 nanoseconds. And the pulse voltage is V naught is equal to 10 volts. So here we have a little diagram or picture of what our pulse would look like here. So we have this as 10 volts and we have this as, 2 nanoseconds. Okay. Now, it says construct a bounce diagram for this problem that extends to a time of 8 nanoseconds. Okay, so first thing we have to ask ourselves, because I'm assuming y'all have an idea about what these bounce diagrams look like, but what exactly are they? Well, they're a way to visualize what the voltage is at different times and at different lengths of our transmission line. So basically, it's asking us, or when we create this, the bounce diagram is telling us, okay, what is the voltage at this point on the transmission line when it first leaves the source? Or what is the voltage at this point when it's reflected off the load? Or maybe what is it at this time, at 1 nanosecond, half of the period, after it gets reflected at the source? This is what it's asking us, or this is what the bounce diagram does. Okay, so let's construct it now. So how do we construct a bounce diagram? Well, first thing we should do is let's just create the outer shell of it. It's going to look like a box, an upside down box here. Okay, and it doesn't have to be perfect, doesn't matter. But it says here, one bounce diagram, or construct a bounce diagram that extends to 8 nanoseconds. Okay, now what goes in here? What goes into this bounce diagram? Well, the first thing I would do is construct our time plots, or our time axis. Time axis is the axis on the left side. This is time, and we want to make sure to say it's in nanoseconds. So, just for us to know here, the bounce diagram on the left, this left wall over here, is going to be our source. This is then going to be reflected on this side, where this is the load. So everything in between is essentially the transmission line. Let me finish that out. Transmission line. So we start at source, we go, and then we get to we go all the way through the transmission line and we hit the load. So what does that tell us from left to right? Well, we're going to see how the wave propagates on this line. Now, back to the time in nanoseconds. Where do we start? Well, we start at 0 nanoseconds, right? We start at 0 up here. Okay, now we look at the time it takes to go from source to load. How long does it take? Well, it takes about 2 nanoseconds, or it takes exactly 2 nanoseconds. So we're going to plot 2 nanoseconds here. Then, to get from load, or I guess from load back to source, it takes another 2 nanoseconds. So 2 nanoseconds plus 2 nanoseconds. Then we plot another 2 nanoseconds. And finally, we're here at 8 nanoseconds. Now, why do I stop at 8 nanoseconds? Well, that's what it asks us. It asks us to plot a bounce diagram that extends to a time of 8 nanoseconds. Another way you will see this is when they use only t's. So this is t, this is 2t, 3t, 4t. Sometimes they'll ask for it in terms of t. Don't be afraid of that. Know what your t value is. In our case, t value is 2. So at 2 nanoseconds, you'll see a T. At 4 nanoseconds, you'll see 2T. 6 nanoseconds, 3T, and so forth. If they say plot up until 5T, that's 10 nanoseconds. Hopefully that made sense for you. Now, what is this axis from left to right? What does that represent? Well, let's think about this. If we say this side is the source, this side is the load, and in between is the transmission line, what does that mean? Well, that's the length. That's the length that the wave will propagate. Now, how do we set that? Well, we can say maybe this is a 0, or even we could just keep doing this, z in meters. This is the way they do it. You can do it this way if you want. Just know this is going to be 0 and this is going to be some L. L is the distance from source to load. That'll make more sense, or it'll, when you have to do like an oscilloscope trace or some sort of voltage with respect to the length it goes down, you will have to draw, of course, a line going straight down, and you have to plot the voltages with respect to that length. But anyways, here, let's figure this out here. Okay. Now, we're almost done creating this, but we need to know what are our reflection coefficients. Now remember, this side is the source, this side is the load. How do we know what well, not really how do we know, but this I'm going to show y'all is the source coefficient, the reflection coefficient at the source, and this is the reflection coefficient at the load. That's where they will reside, essentially. Now, what are they? Well, if we remember from before, and it's okay if you don't, for real, because there's quite a lot of equations to remember. The reflection coefficient at the source is equal to the source resistance minus the impedance, the characteristic impedance of the line, divided by the source resistance plus the characteristic impedance of the line. One quick way you can figure out if it's 0 is, does the characteristic impedance here match the source resistance? In our case, it doesn't, so there will be some reflection. And we can say then that this is equal to 50 minus 75 over 50 plus 75. That should give you a negative number, and that number is negative 1 over 5. So we're going to let this be negative 1 over 5. What about the reflection coefficient at the load? Well, now this is going to be the exact same equation, except we trade out the source resistance with the load resistance. That should be a ZO. And again, now we use the load resistance, which is 25 minus 75 over 25 plus 75. And this is equal to negative 50 over 100, or negative 1 over 2. So this is negative 1 over 2. Great. Why did we solve for that? That seems pointless, right? Well, what we're going to end up doing is we're going to create this bounce diagram. We really need those values. It'll make sense now. So let's first think about this. What will be the voltage at 0 nanoseconds? It has to be 0 volts. There's no reason it shouldn't be 0 volts at the load side. Now, what you're going to do is you're going to create these lines, these arrows. This, of course, is going to be at, 2 nanoseconds? It takes how many nanoseconds to get from source to load? It will take 2 nanoseconds. That is where the first arrow stops. It takes 0 to 2 nanoseconds to get from source to load. So how do we know how much the value of the voltage is? Well, we know that the source voltage will end up being the incident wave. Do we remember what the incident wave here is? It's V plus. Now, it's not just our voltage. It's not just V naught. This is going to be equal to A times V naught, and of course T minus Z over CD. So what is A? Well, A is going to be equal to the characteristic impedance, so 75, divided by the source resistance, 50, plus 75, times V naught, 10, T minus, well, we start at 0 position, so this is going to be 0, so this is no phase shift. Don't get confused about this. You don't really need to know how to do this. It'll make more sense when you are plotting on here. You really just need the magnitude. So you really need just A and V naught. So what is A? That is 75 over 125. Let me check it real quick. 75 divided by 125. 3/5 times 10 is going to give you 6. So 3/5 times 10 is 6 volts. So V plus, that value will go right here. 6 volts. Let me make that a little thinner then. 6 volts. So what you're going to do is you're going to take 0 plus 6 volts and put it over here. This is 6 volts. And what you can do is you can create this dashed line. So from 0 to 2 nanoseconds, after the wave has passed these points to the left, there will be 6 volts. Now, the wave is going to start coming back here. It's going to start coming back right here. It's going to hit 2 nanoseconds, or after 2 nanoseconds from the load, it's going to reach back to the source. So it's going to be reflected back to the source. So if another way you can imagine this is, imagine you have your source or your wave here, and it gets hit, and then it's being reflected at a smaller amplitude, and it's going back this way. This is what's happening. Of course, it won't be on the bottom. It's just going to reflect back here. But that's what's happening. So at 2 nanoseconds, this is 2 nanoseconds here, it'll hit the load. Then, going back, it'll take another 2 nanoseconds to get back. This is what we're plotting. Okay, so what goes here? What goes in this area? Well, this is still 6 volts because you have no arrow pointing in between these 2 points. So you have 6 volts in this entire triangle. But what about over here? What about across the arrow? Well, think about it in this case. We have V plus. That's our incident wave, the wave that hits the load. We are going to multiply that by the load, or the reflection coefficient at the load. This is the ratio to which the incident wave, or V plus, will come back. So it's being reflected, and we need to know by how much. Well, it's by L here, lambda L. Okay, what was lambda L? Well, lambda L here, and this is the reason we have these, so it's very easy for us to see. It's -1/2. So what goes here? This is 6 times -1/2 is -3. So now what we do is, well, we end up adding, and let me erase this and replace it with a -3. Hopefully y'all got that. If you need to press pause, press pause. This is -3 volts. So now what we do is we do 6 plus -3. Always do plus. 6 plus -3 is what? 3 volts. Okay, perfect. So we have, we can then again draw our dashed line. We don't need to, it doesn't matter. But this is 3 volts. Let me do that in white. Because 6 plus -3 again. 6 plus negative 3. And now what we do is we have our voltage there. We do the same thing. Imagine this is actually 6 nanoseconds because it definitely isn't. But remember, there's no arrow in between, so the 3 volts just drops down. Okay, so now, again, we have negative 3 volts above, and now it's being reflected off of the source. So now what do? We multiply by the source coefficient. So just a brief overview here. When the arrow hits this wall, it's going to be multiplied by whatever this factor is. And the same thing going back. When the arrow hits this wall, it's going to be multiplied. This will be multiplied to whatever this is. Or not this, sorry, not this. Wait, yes, that. To make sure here, negative 3. Then that'll become 18 over 5. Yes, it is this, sorry. You multiply this, or I guess this, by whatever the coefficient is. So if you want to imagine whatever's on this arrow will be multiplied by that coefficient, the wall, the coefficient of that wall. Okay, sorry if that was confusing. So now 3 times negative 1 over 5 is 3 over 5. So we have 3 over 5 volts. Now we add. Remember, again, we add. We go across the arrow. 3 plus 3 over 5. Well, 3 is what? 15 over 5 plus 3 over 5. That's 18 over 5. So you add that and you get 18 over 5. You do this the same way. You keep this here. And now you redraw here. Imagine that straight. And we take 3/5. It's going, and it hits this wall. The coefficient at this wall is negative 1/2. 3/5. 3 over 5 times negative 1 over 2 is what? Negative 3 over 10. So we have negative 3 over 10 volts on that line. And then what we do is we add 18 over 5 plus negative 3 over 10. So that's 36 minus 3 is 33. So we then get 33 over 10 volts. And we just finished the bounce diagram, or the first bounce diagram. Notice this, I said first. We'll move this down so we have more space. So because this is a pulse diagram, or a pulse wave, what's going to happen is that pulse, the end of it won't end. It won't end here. It'll lag a little bit. So what's going to happen here is it's going to lag by how much? By this width. So what we need to do is plot another bounce diagram after 2 nanoseconds. So where will it start? Well, it's going to start at 2 nanoseconds. So what will happen is, if you want to really understand this, this is width W. W can be anything. In this case, it is 2 nanoseconds. So we're going to plot at 2 nanoseconds so we can make this 2 nanoseconds there. Now, what do? Well, this is 4 nanoseconds, 6 nanoseconds. We can say this is 8 nanoseconds, and we can make this 10 nanoseconds because it wants it 8 nanoseconds. I mean, I guess we could stop there, but it doesn't matter. But I know for certain I do not want to have to do all of that math again. Luckily, it's the same graph. Nothing changes. Nothing changes. It is just the time at which it changes. So what can we do? Well, I'll tell you what we can do. All we have to do is plot this again. We can just do this. Make sure if y'all can make this straighter than me, because I don't draw very straight lines. It's 8. Oh my gosh. Yeah, that's good. There we go. Then we take our values here. So this is 6. So 6 goes here. It starts off at 0. So 0 goes here. The value after 0 is what? 6 volts. After 6 volts, it goes down 3 volts. So this is 3 volts. If you notice, all I'm doing is taking these values and moving them over. It starts at 0, 0. Then you add 6. Let me wait for that. Then you add 6. Goes right there. You take this next value, 6, put it right there. How much does it go down by? -3. Put it there. Then you have 3 volts. So what goes here? What? This 3/5. So this is 3 over 5 volts. 3 minus 3/5, or 3 plus 3/5, sorry. 18/5. Wow. So once you graph one bounce diagram, you really don't need the other one. You just make another, like, I guess, picture of this picture frame, and you literally just copy the values. No need for extra calculations. Now, you're done. You're done with part A. I hope this was easy, or maybe not easy, but better and easier to understand about how we found these values. And I'll write down the equations here if I didn't already. Oh, I did. Here. And I hope y'all can understand you really don't need to memorize. I guess you would need to know how to work these equations, but after that, you don't need to know the equations for the values in here. You really just need to know which wall you're bouncing off. Are you bouncing off the load wall, or are you bouncing off the source wall? If you're bouncing off the source wall, you multiply by the coefficient at the source. If you're bouncing off the load wall, you're multiplying by the coefficient at the load. So this is part A. Now part B, let's look at this. Part B is, let me see here. Make an accurate snapshot of the plot VZ voltage on the line at t is equal to 2.5 nanoseconds. Okay, and then indicate which directions the wavefronts are moving. So 2.5 nanoseconds. So we're taking a snapshot. So we'll write this snapshot. And we're saying at a specific time. So time will stay still. So time will stay still and Z will change. So we have Z and what was T? 2.5 nanoseconds? 2.5 nanoseconds. So what we're trying to find is voltage with respect to the length of the transmission line, or Z. Okay, so what do we do here? Well, first let's figure out where 2.5 nanoseconds is. 2.5 nanoseconds is maybe like right here. Okay, so let's create a dashed line here, all the way across. So you really want to make it all the way across. So I'll even draw a dark line instead as dashed. Okay. So your lines may not be perfect. It does not really matter. What you will do is you will plot. I guess there are two ways you could do this. You could plot two different voltage versus length plots and then subtract them from each other. Or you can make one using values you know are true. Now, for this video, I will make two, just so y'all can see exactly how this goes. So let's make a voltage versus length graph. So we'll call this Z in meters, and this is voltage, VZ, right? So for this first one, what do we start at? Well, at 0 nanoseconds, or at 0L, which is LG, we start at 6 volts. So what we'll do is we'll call this 0L. Then we'll say L over 4. Then L over 2. Then 3L over 4. And finally L whenever you get to the load. So just so you know, this is source and this is load. But how do you know where the voltages are at the different lengths? Well, that's what we're going to get into. This is where, there can only be one of two different answers when you're doing this. If you see that your line is crossing not halfway, but above halfway, you assume it's L over 4. If it were to be at 3.5 down here, it doesn't cross it halfway between L and L over 2. And remember, this is L over 4, this is L over 2, and this is 3L over 4. Because remember, this entire thing is the transmission line from 0 to L. So where does my green line cross our red line? Right around here. It's close to 3L over 4. We can just leave it as 3L over 4. So the voltage is at 6 volts until 3L over 4. So all we have to do is we can make any arbitrary point 6 volts, and we'll let that be up until 3L over 4 there, right? Good enough. Now, after the 6 volts, how much does it go down by? What is our new value? Well, here, it then reads, 3 volts. So we go down to 3 volts. So now we can make this 3 volts, and we can say go straight down here, and it ends here. This is for original, I guess you could say original bounce diagram. Now you need your shifted. So now you need a shift diagram, right? So you create one more. Okay, it doesn't have to be perfect. We just have to make sure to get this done here, Z in meters. Now, we look at our shift diagram. Remember, we'll say this is L over 4, L over 2, and 3L over 4. So again, we go here, and now we reach, this is about L over 4, so we're at, what is the voltage of this line? It's 6 volts. 6 volts up until L over 4. So we'll try and keep this in line right here. This is L over 4. And now this is L over 2. We'll make this a little longer, actually. Then we have 3L over 4 and L. So we said it was 6 volts up until L over 4. Sorry about that. We have 6 volts up until L over 4. Now, what do we have? Oh my gosh, it's 0 volts, right? Who cares, right? It's going to go all the way down to 0 volts here, all the way to the end. It will not gain anything. It's going to be 0 volts all the way to L. Now what you do is you subtract. So now you can subtract the original minus the original and the shifted diagram. So original minus shifted diagram. From 0 to L over 4, if we subtract this, what do we have? We have 6 volts minus 6 volts at 0 to L over 4. Well, that's 0 volts. We don't have to do anything for that one. 0 volts. Now, from L over 4 to L over 2, original minus shift. Well, that's 6, again, minus 0. Okay, so now we go from 0 to 6 volts here to L over 2. And now L over 2 to 3L over 4. I'll draw lines here, L over 2 to 3L over 4, about there. That's, again, 6 minus 0, so it stays at 6 until 3L over 4. And finally, we look at 3L over 4 to L. That's 3 minus 0, so we go down to 3. We'll make this 3 volts. It's arbitrary, you can pick whatever you want, as long as it makes sense, right? So L. And this is our final snapshot. So this is our snapshot here. But it also says the direction. That's going to be a little weird, right? Well, not so much, actually. So we have to think about the direction of this. What is the direction of the original time plot? What does direction even mean? Well, the direction results from where the arrow is pointing at the time of the at the time, literally. So at 2.5, or from 0 to here, what voltage are we going off of? We're going off of 6 volts. Sorry if that was a bad question. That was a bad question. Terrible. Oh my gosh. So at that time, from 0 to 3L over 4, we're going off of the voltage from this arrow. We are not going off the voltage from this arrow, even though it's closer. That arrow has no effect on the source or on the left side of this arrow, right? The voltage or the arrow has no effect on the left side of the voltage. Only until you get to the right side does it affect. So from 0 to 3L over 4, you have 6 volts, and the 6 volts here is going to the right. So on the original graph, from 0 to 3L over 4, we are going right. So we're going this way, from 0 to 3L over 4. But after, this is where it's important, after it crosses at 3L over 4, we hit this new arrow and it's going left. So now, because we bounced off the wall of this load, it hits the load and now it's going left. So what we're going to say here is from 0 to 3L over 4, we're going right, and from 3L over 4 to L, we're going left of the original. What about the shifted diagram? Let's look at this. Again, we look at the way the arrow is going. From 0 to L over 4, right? Because this is what we have here at 6 volts. The arrow that accompanies this 6 volts will be the one going right. So we have this. We have right. It's going in the right direction. Now afterwards, after it goes to this new 6 volts, it doesn't have any direction, really. We can just say it's right. It doesn't matter. Because it's 0 volts. There's nothing there. So really, you have like a standstill. There's no motion. Bro's got no motion, literally. There's no motion going on there because there's 0 volts. So what we're going to do is whenever we subtract from 0 to 3L over 4, what are we doing? Well, we're going right on both sides. We're going from 0 to 3L over 4, we're going to the right. 0 to 3L over 4. But after 3L over 4, we're going left. So after 3L over 4, we're going to be going left. 3L over 4 to L. This is the wave direction. Now, what if whenever you subtract, the arrows were going in the opposite directions of each other? Well, what would happen is when you subtract them, you take the one that has the largest magnitude. So say, for example, on this one, exactly here, instead of it being 0 volts from 3L over 4 to L, we had something go like this. It went back up to 6 volts, but instead it was going to the right. We would do what? 3 minus 6. This is negative 3 volts in the right direction, because the 6 volts is higher in magnitude. So it takes accountability, or I guess you could say it takes over. So you would be going in the right direction. You'd be going right instead of left. Hopefully that made sense. But yes, that's how you would do it. So 3L over 4 to L. And that would be your answer. And there we go. We're done with the snapshot. That's part B. So hopefully this was okay, and hopefully y'all could understand what I went through on this one and how to create bounce diagrams, because that is very important for our exam. This will always be a third question. So thank y'all for listening. I know this was a little bit of a longer video, 36 minutes. But thank y'all, and y'all have a good night.